And so there have been there has been technology by Lytro, for example, to use microlens arrays to reconstruct the light field to then, essentially generate a photo that you can have any depth of field and that you can construct sort of any focal point. And you could also use that to reconstruct 3D information. So I'm wondering if you thought about playing not only with the patterns where you learn sort of your irregular microlens array, but playing around with your diffuser, which is a microlens array, and making this in a certain shape.
Sure. It's not a microlens array.
I see.
It's a random lenslet array. And these are very different because the regular grid of microlenses produces patterns that are periodic, which have redundancies. And so to avoid the redundancies, light field people match the apertures, which is why light field cameras are not usually lensless. They have aperture lenses with apertures on them. And so actually the whole project started as a posing to my grad student on his first day. Could you make a light field camera with this diffuser because it's cheaper and easier and it doesn't need to be pixel aligned? And more importantly, in a microscope, you can change the aperture without having to change the microlens array, which is extremely limiting for a microscope to force the aperture to stay the same size always. But actually, we realized along the way that that the randomness helps you a lot because it enables this sort of the randomness means that the response is different for every point in the scene, and so we don't have this redundancy problem, which means that we can do compressed sensing with it. And so actually, we do 3D. That was our first paper on this. We also do like super resolution in time because we can do this sort of compressed sensing by putting sparsity priors, which you can't do with a regular grid array. And the other answer is that yes, we are doing end-to-end learning of the diffuser surface design. And actually, these random lenslets that we use now, mostly like our best ones are like we're smashing ball bearings into copper and using that as a mold. And the super fancy fabricate the perfect ones are really not that much better yet. But we're still working on this because fabrication is a real issue here. There's not a lot of fabrication techniques that can handle like the sizes that we're looking at. So it's something that we're definitely working on. But it hasn't been super impressive to, like the learned designs haven't been impressively better than our heuristic ones, which I think only says we're good at the heuristic stuff.
Essentially just use off the shelf instead of like making your own distribution. I guess they're small with the size of my.
So we sometimes use off the shelf, but we are trying to make our own now. They're hard to fabricate exactly what you want perfectly.
I don't know how to phrase this question, but one word that didn't come up today in this session was causation or causal inference. But it felt like a lot of things people were doing kind of fall into that category. Like, Josh, is it not true that somehow the fundamental assumptions that allow the self-supervision to work have something to do with causal inference because of causal conditional independence? And I wanted to just generalize my question a little bit because it feels like Ben's magic of getting things for free also had a causal inference aspect to it. And it also felt like Laura's capability of simultaneously calibrating and getting a higher resolution image also somehow emerged from causal structure or like the causal independence of the calibration issues in the scene or something. Anyway, my voice didn't go up at the end.
Well, in response to that statement, yeah, I think the simplest, all I need is independence, conditional independence, but like the reason that that's there usually is a causal structure where you think of whatever you're imaging as being the cause and then the noise happens far downstream from that. And the place this fails is when the graphical model, the causal diagram is more complex, and then that will leak through. There was some work by another group that sort of showed that this will remove the independent part of the noise, and what you're left with is like the beautifully structured version of the problems with your imaging apparatus, which you can then deal with later.
No, it's exactly the same thing. And in fact, we have another part of the problem, which is that, like in the magic that I showed, you need the statistics to be really the same. So it's like the analog is in your images. You need, like in the future, the noise to noise. The two images better be exactly the same underneath before the noise. Otherwise, it won't work. So we need the same thing. But it's the same causal structure where you expect that the noise is sort of generated afterward. It has nothing to do with the actual image itself. That's critical.
Okay, thank you for the talk. I have a question for Sergey. So first question is how to avoid random seed overfitting in practice, and the second question is for the maximal entropy method. So can we just add the entropy bounders to the policy gradient and not anything with the Q function? The third question is, okay, do we need to annealing the weight for the entropy bounders in practice? Because at first we need to explore the, we need our engine to explore our space, but at the end, I think the policy will focus the most valuable trajectory. So I think that we need to annealing the weight for the policy, not entropy bounders. Thank you.
Okay, so the second one is easy. Yes, and in fact, that's a very reasonable way to do things. So there's sort of the objective and the mathematical framework, and then there's the algorithmic instantiation. And it's very straightforward to instantiate it as a policy gradient algorithm. So absolutely. The third one, so it kind of depends on your problem formulation. Like in some sense, the point behind maximum entropy RL is that you're sort of redefining what it means to be optimal. You're saying optimal means you're covering all the high reward stuff rather than the best stuff. Now in practice, you might not actually want that, in which case you could just heuristically use the method as a way to get a better solution and then gradually switch back to regular optimality. And that's very reasonable. For the first question regarding random seeds, you should, well, okay, how can I put this? So random seeds exist in a computer. They don't exist in the real world. Well, okay, maybe somebody with like better knowledge of quantum mechanics than me can correct me on that. But it feels like an issue that sort of exists when we play with simulated benchmarks. But it's not really like that's not a thing in the real world, so I'm not as worried about it.
One more question. Yeah.
This is also for Sergey. So the entropy has the units of bits, and the Q function has the units of reward. So those two are, there is a dimensionful hyperparameter that you omitted, and of course your group has proposed heuristics for tuning that parameter. Could you comment on the recent progress on that?
Yeah,
please?
so this is actually, I'm really glad you asked that question, and I think that it's sort of, to me, I think it reveals the possibility of a mathematically beautiful future interpretation of reinforcement learning that we don't yet have, because you could say, well, okay, if the units don't match, what does that suggest about what rewards actually mean? Perhaps rewards are actually things that should be expressed in units of log probability, and you can in fact pose questions like that. You can say, well, maybe your reward is your log probability of achieving some outcome. And then actually everything makes sense. So you say that what you're trying to do is you're trying to maximize your probability that you will, I don't know, earn $1 million, and then you can express the probability of that event using your favorite probabilistic model, and everything actually makes sense. And we've done a little bit of work on this. We have a paper called Variational Inverse Control with Events that basically proposes doing away with reward functions and instead using log probabilities for everything. But I think that there's potential for a lot more work in that area, and I'm pretty excited about that.
One more question in the back. Since you had me fix the microphone, you deserved it.
So reinforcement learning tends to be pretty data inefficient. When you add the entropy to the models, how does that affect the efficiency of the learning algorithms? And are there ways to include that concept of entropy while having less of an effect on the efficiency in training?
Yeah, so I guess there's a sort of an empirical answer to this, and then maybe a little bit of like conceptual hand waving that I can do. So the empirical answer is that it appears to make things better. But there's something a little bit complicated there because, well, maybe what's really happening is that it's doing a better job of exploring and then later on wasting a bunch of time, but the overall results look better because that initial phase is better. So empirically, it seems to be better. Conceptually, well, it's very difficult to disentangle there's like a good thing and a bad thing. The good thing is that you're exploring better. The bad thing is that you're doing a bunch of random stuff. So you probably pay a price for doing a bunch of random stuff. But I think it's actually very hard to disentangle the effects of these. You know, in the end, I think for now it has to be an empirical question. There is a little bit of a theoretical analysis of these kind of softmax style policies from Michael Lippmann's group, but I don't think they have any like particularly convincing results in that regard.
All right, this one's for David. So it's really cool to see the spectral learning, like disentangling the eigenfunctions. Also seemed complicated. So I understand PCA a little bit better. So there's been two questions. One is, there's been recent work showing that if you do some L2 regularization, then you sort of do learn to order your eigenvalues, and you sort of split out eigenfunctions there. I was wondering if that worked in this complicated context. And then going backwards, can you do this clipped gradient thing to just make a linear autoencoder learn to do PCA?
Yeah. Well, we're not trying to do sort of autoencoding here because it's, I mean, part of the reason we called it spectral inference networks was it's purely inference. It's going kind of entirely in one direction. But you know, your choice of kernel could include things that look like sort of a simple PCA type type thing. I mean, kernel PCA is sort of one of these classic nonlinear dimensionality reduction methods. So what we were kind of presenting here was kind of just the most basic framework and kind of working out how to train that. So imagine there are, I'm sure, all sorts of additional regularization terms you could probably add on top of that, and maybe start even talking about, you know, there are close relations between spectral methods and diffusion, and maybe start talking about diffusion of vector-valued quantities instead of scalars and things like that. So this was kind of, sorry if it came off as a little complicated, because I think it's, you know, with enough practice, it'll. But I think that there are many more bells and whistles that could be added on to try to impose certain kind of structural constraints. Yeah.
It also seems that you're basically learning in Koopman embedding. So this whole connection to the Koopman world is basically just learning a linear operator.
Yeah. Well.
The whole game in that field. So I think
yeah. I guess we're assuming we already know the linear operator and we're trying to decompose it, but I bet there are probably very interesting connections there. Would be very interested to look deeper into that. Mm-hmm. Mm-hmm. Yeah, definitely.
All right, last question.
I have a question for David. So for your spectral method, you want to minimize the first n eigen values, right? Why you want to? First question is why you want to separate them? Because if you do not separate them, it's just a summation. I think so this is my confusion. Second question is how this will helpful to the RL, because can I think your method is kind of getting a PCA, get a latent embedding for the environment, then you do some RL algorithm on top of the embedding, so you just do the yeah.
Sorry, could you repeat that last bit? You add what was that you add on top?
That you change your observation. You change so you map your observation to another latent embeddings.
Yeah.
Then you think that will be your state. Then you do your favorite IO algorithm on top of that. On top of that, you think that your observation is no longer the image base, but your latent.
Yeah,
state.
Yeah. So I think this is maybe sort of related to what Nathan was saying about these Koopman operators, that we are, in some sense, trying to map things into a space where not only are they more sort of interpretable, sort of from a human judgment, but also where you might be able to, say, do rollouts for sort of some kind of planning, and it might be easier to model the dynamics in this latent space. And people have looked at other sort of related methods. I didn't have time to get into the talk, but other methods that have this flavor of a kind of contrastive learning or learning and embedding, where things like contrastive predictive coding or time contrastive networks, where they have shown that you're able to do sort of interesting robotics tasks using these learned latent representations. So there's definitely opportunity there. As for why we want actually to get an ordering rather than just sort of minimizing kind of everything together, there are probably some tasks where you don't actually need the ordering. I think one of the nice things is that you don't have to really pick the dimensionality ahead of time. You could just sort of train things with as many dimensions as you want, and once you have an ordering, you can say, all right, I'll just keep the first 5 dimensions or something if those turn out to be the useful ones. So you're kind of learning a hierarchy of embeddings instead of just one single embedding. So I think that has some nice properties potentially.
All right, let's thank the speakers in my session.
Thank you very much. Let's give a round of applause to all the speakers from today. I'm not sure I did the exact count right, but there were 26 speakers. So I was absolutely blown away by the talks, not just in the content, but also the interconnects between fields. I hope over our reception, which starts in about 15, 20 minutes down the hill, that you'll also make some connections with people that you didn't know already before today. I also think we've discovered that 16 minutes is like the magic number for the length of talks, because it's like optimally compressive. Like, we got a lot of information with very little noise. So thanks again to everybody. For those that are coming back tomorrow, we are starting at 8:30 sharp back in this room. Again, the reception is at Gather in the patio. It should be a beautiful late afternoon here. For those that don't know how to get there, it's basically down the hill. It's on Oxford and Alston. Feel free to grab somebody local and walk down with them. But grab your stuff, and we'll all start walking down en masse, and see you in a little bit. Oh, we've got one more announcement?